Okay, this is my presentation about acoustic emission coupled with thermogravimetry, which is a very innovative solution for the study of high temperature corrosions of metal alloys and composite materials. I am Véronique Perez. I am now working at Orano as a nuclear fuel fellow expert, and this work was done when I was professor at École des Mines de Saint-Étienne, which is a graduate engineer school and research institute. With this work was funded by some fund coming from the French government and with some industrial partner as BFP Énergie Nouvelle and IRSN. This is a summary of my talk. I will detail the context and some detail of the equipment we use for this study. And I will show you 4 examples. The 2 first examples are industrial one for zirconium alloy oxidation and meltite dusting of iron, and the 2 second one have more theoretical ones. One is for the composite oxidations, and the second one for the mask alloy oxidation, and we will see the methods, the limitation of the method we used. And then we will have a conclusions. For the concept, we were asked for from some industrial to study the high temperature corrosion of their equipment and to anticipate as we can the breakdown of this equipment due to corrosions and to predict if you can the lifetime of this equipment. I show you in these pictures 2 examples. The first one is a catastrophic corrosion of by metal dusting of tubes in the petrochemical industry under reducing atmosphere at high temperature. You can see some holes in these tubes, and it's very, very detrimental conditions. The other one is a catastrophic oxidation of zirconium alloy in case of a nuclear plant accident. In this case, you can have also an oxidation, very aggressive oxidation of the nuclear fuels tubes, and propagate the accident in all the plants. We can see that with holes and cracks, it can generate some electric waves and propagate. And if we use acoustic emission, maybe we can have the moment of these corrosions. And by monitoring the installations with acoustic emission acoustics, it will be very fruitful to know about corrosions. So we decide to make a specific tools and to make the association of acoustic emission with thermogravimetry. We study normally high temperature corrosion with thermogravimetry by weighing samples, and in the same thing we want to attribute eventually events due to corrosion phenomena. So we design special equipment adapted to severe conditions. If you look at these graphs, you can see here some bursts coming from the samples, and these waves are so transferred to a waveguide connected to the weighting systems. And if we make an amplification of the noise we heard here in the sample, we can acquire and process the data to be able to have the informations. So this is a drawing of the system. You can see here the 2 furnaces, the reference one when we put nothing, and the second one when we will put the sample which will be submitted to the corrosions. And here you have a waveguide. In the upper part of the system, you have 2 metallic supports, and in ones we put a sensor, which are piezoelectric ceramics, and preamplificators, which can permit to record the events coming from the samples and treat the data. You have also some gas inlet here and a gas outlet outside at the bottom of the systems. I will show you some more detail of the system. You can see the upper part of the equipment, which is the Saturn ones. And in this part, we put here some special device. This is a sensor we put on the metallic support for the weighting here. And the preamplificator is here. And you saw some copper tubes, which can permit to transfer the noise in the piezoelectric system to electric system preemply here. At the lower part of the system, we have the high temperature, so we decide to use a waveguide, which is in aluminum. And you can see here the small sample we have in these systems. If I show you the wave specification, it's a little bit complicated because the system has to be very inert, chemically speaking, to the environment, to the samples. It can have to sustain high temperature, around 1000 degrees C, and it's have to be a very good for the wave transport. So this is a property of the alumina gate, so a very good electric wave propagation speeds, a low amplitude loss, because we generate here at the bottom of the waveguide the noise, and the wave will be transferred to these tubes, aluminum tubes, to the top of the system. So it was a huge work to define and to design this waveguide, but finally we succeed to do it. If I show you an event acoustic image, it's very complicated because we have a lot of data when we record this acoustic emission burst. We have the duration, we have the salve amplitude, the numbers, the absolute energy, the frequency. We can do a lot of things. So we applied a treatment for each experiment we do to be able to analyze these events. First of all, before doing everything with a system, we have to calibrate the acoustic emission system. The test is Zunison test. We do it at room temperature, and we have to verify that the sound coming from the sample going to the top here, close to the piezoelectric system. So we do that with a pencil tip. We break on different surfaces. We break it on the top, close to the piezoelectric system, and we also do on the metal samples in order to be able to know that if we break the system, the tip of the pencil here, we heard something here at the piezoelectric after preamplification of the noise. And we do that, and if we succeed, it's okay, we can begin the experiment. So I will begin with the first example, which is zirconium alloy oxidation. We test zircaloy cat, which is an alloy with 1% stins, and we test it at 900 degrees C under closed air condition. What I mean by air is that we have not only oxygen but nitrogen. And in this case, we have a special component of this alloy because under air, the oxidation is enhanced by the formation on zirconium nitride, which are on the interface here from the metal to the oxide, which has been formed during the corrosion. In this graph, you can see here the mass gain of the sample during the experiment. In red, you have the temperature curve, and in black, you have the oxidations. At the beginning, you have a very normal oxidation behavior, which is a parabolic one, but after transition, a breakaway, here you have a quick increase of the mass gain. So it's very critical. Why? Because we have these mechanisms. I will not explain in dating this mechanism, but you can see in gold, this gold precipitate with our nitrate. They are here at the interface of the metal oxides interface. And this nitrate is very unstable, and with oxygen coming from the external part of the tube, due to the porosity, it can relax oxygens to make the corrosion here of the metals. And there is an autocatalytic effect of the nitrate precipitate. So we have done the treatment under air at high temperature or zirconium alloy, and then we have recorded the mass gain, but also the acoustic emission events coming from the sample. Before that, we have made some blank tests, because that is very important in acoustic emission studies, that we have to attribute the events coming in the experiment from the noise due to the heating of the furnace, of people coming in the room near the experiment, and the events only coming from the corrosion. So this is a picture of the graph we have during the plant test. And here you have the picture of the sound we record during the corrosion experiment. So we have some methodology, which I will not explain here, to extract from the experiment of corrosion the noise coming from the environment. It's easier to do. And then we have here, after treatment, only the noising coming from the test. And you can see that here, this is a representation of the kinetic mass gains, different directly the mass gain. You have a first increase parabolic one, the transition, and then again the increase of the mass gain. And you can see here that the noise only come after the breakaway, that we have to have cracks to make the noise, and after the breakaway, we have a first domain here that you can see the increase of the noise in the samples, and then during the cooling, which is in green here, you have a lot of noise due to some cracks. And in this case, it's the first time we have identified cracks during the heating, the corrosion, and cracks during the cooling. After that, we have to attribute the crack, and we see again the picture of the corroded samples, and we can attribute some cracks due to the cooling and some crack due to the corrosion. So it's very interesting to have these pictures, and we use it. It will be useful to study the corrosion of zirconium alloy with these systems. The second samples is in the petrochemical application, and this corrosion is called metal dusting. Metal dusting is due to the formation of dust. This is a dust. You see a powder, black powder on this the waveguide. You see also this black iron sample. Due to reductive conditions, you have a formation at the beginning of cementite, and then a decomposition of this cementite at the surface of these irons. And so we will try to understand if this system creates some noise, and if it can be recorded in the industrial conditions. So this is a metal dusting mechanisms, as I show you for the zirconium. In this case, we began with oxidation of the sample because it's an industrial conditions. We have a iron oxide at the top surface of the iron, which is here, And then due to reductive condition, isobutan, we have some reductions of the iron we previously formed, and coming some holes here. And then if we make again the reductive conditions, we have progressively insertion of graphite of carbon inside the iron, and a deposit of graphite at the surface. And then we have some cemented formation, but it's not stable in this atmosphere. And we have production of carbon, which is coke and nanotubes of carbon, and the decomposition. So we hope to have some acoustic emission to these systems. So I show you the global experiment we have done in the SEP equipment with a wave mass gain, which is in blue here in this system, and the sound, the amplitude of the burst we acquire during this experiment. First of all, we make the heating under helium, and then we in situ make the oxidation under oxygens, which is a parabolic. When they change the atmosphere, because we don't want to have oxygen and isobutan in the same atmosphere, it's very dangerous. So we do that under helium, and then we began to make treatment of the sample under isobutanol plus hydrogen and helium. And so we have this mass lost, which represents the reduction, and after a linear mass gain, which is very interesting here, a linear mass gain of the samples inside the waveguide, and we began to hear some noise due to the corrosion, to the insertions. So this means it's very interesting because we have quite an inductive time here, and then the corrosion and the production of noise due to the cementate decompositions. If I can show you some picture of the sample we have, this is iron, and with iron oxide on the top surface and more oxides, irons in the center. After reduction, you have the reduction of this internal layer of iron oxide. After carburation, you can see is just before we can have acoustic emissions. You have the beginning of the increase of carbon inside the layer, and after that you begin to see here a clear view of what happened with COX. And so what we can see here is that all these steps are without any acoustic emission. They are not so dangerous, and beginning with the real metal dusting process, you have some noise, so it can be recalled by these systems. Now I will go to the third sample, which is a theoretical one. So we decide to study an interesting composite, which is made of zirconia, YZS zirconia, stabilized zirconia here, which surround stainless steel particles here. Well, you can see also some holes, but it's very dense. And what is very interesting is that you don't have any cracks in this composite. It's very clean, and it was very interesting to see that if you look closely at the interface in between the stainless steel particle and zirconia, it's a very clear, there is no oxidation layer, which is typically appear with stainless steel powder. So all the chromium oxide present at the surface of this stainless steel is dissolved in zirconia. If we do the treatment under air at high temperature, 800 or close to 800, under oxygens, you will see two things. We have in purple here different tests we have done with the composites. It's not so reproducible, but it's quite the same behavior. So you can see here a very big mass gain of these systems. But if you look at this blue line, which is the powder mass gain, it's very, very low compared to this composite behavior. So why do this happen? If we look at the sample after corrosion, you can see here a very interesting pictures. You can see that all the zirconia, which is in this light gray, is cracks, and the cracks are coming from each particle of stainless steel in more gray here, and that you can see is it's around each of these particle, this stainless steel particle, you have a gray, dark gray color, which is a corrosion, oxidations of the particles, the stainless steel. And if you see the external layer of the composite here, and mainly near the interface of the stainless steel, there is no big corrosions of these systems. That means that we have an internal growing of the layer in the metallic, in the stainless steel module, and then we have a catastrophic oxidation of this particle inside the composite. And we produce some chromium oxide and many iron oxide layer, which conduct to this cracks system, and with a high mass gain, much more than the powder one. So we decide to record during the experiment the noise, the events, the acoustic events. And you, on this graph, you are, this dark line is a mass, is a temperature. You have this curve is for the mass gain, which is a parabolic one. And here you have a burst we require. And in this case, not like the two previous one, you can see that since the beginning of the experiment, we have noise. That means the cracks are formed at the beginning, and they are due, the cracks and the noise are due to the constraints of the precipitate of the layer we form around the precipitate, and we calculate what is the layer, the thickness of this layer, to mean some constraint that can provoke some cracks in the sample. And this layer is very, very thin. So it's around 0.05 microns. And if this layer appears inside the sample, you can hear some noise. This in another case that we can follow the crack in the system. So this is the mechanism. I will not explain in detail, but we have this internal oxidation growth of chromium oxide, but is not very protective. So that means that after that, some iron can go outside the precipitate, and with the oxygen coming from the zirconia, which is the easy transport of oxygen in zirconia, you can have a growing oxide of iron and chromium outside the particle, and the cracks are coming from this external layer. The fourth sample is the oxidation of a mask alloy. Mask alloy are niobium-based composites, 46 niobium, 25 titanium, 8 hafnium, 2 chromium, 2 aluminum, and 16 silicium. In this case, these alloys are very interesting because they are also quite a composite with different phases inside. And when you make the oxidation under air and oxygens at high temperature, you have different behavior. And you can see here some different behavior. You have the oxidation of one internal oxidation of one part of the phasing, and the second one is not oxidized, but you have some cracks coming from these different phases. And so it can be possible also to follow the oxidation by acoustic emissions. That we do that. And in red, you have the mass gain, no, in blue, sorry, you have the mass gain, and in red here you have the cumulative signal of acoustic emissions. And you can see that in this case also, like the previous composite, you have the burst directly at the beginning of the system. You can see also here a strange effect that after a certain time here, after 5 hours, you don't have any acoustic emission signal. Why? This is the same in this graph. Because you produce some dust and you lost the contact in between the sample and the waveguide. And so it cannot be possible after a certain time to obtain a signal in between the sample and the waveguide. It's one of the limitations of this method. If you don't have a good contact in between the sample during the corrosion and the waveguide, the sound cannot propagate via the waveguide, and so you cannot record it. So to make a conclusion to my presentation, so I show you the equipment we designed to have some information of mass gain and acoustic emission analyzing during high temperature corrosion. And we do it, we can do it until 1000 degrees C. The important thing that all the electronic part of the system must be placed at the core part. And we have to be careful about that. And I show you some different examples. And when we know about the mechanism which are implied in this corrosion system, as in zirconium or as in iron metal dusting, it will be able to follow industrial equipment only with acoustic emission, which is a very nice equipment to allow the diagnostics. In this case, you will have to have a waveguide which can conduct or transfer the elastic wave coming from the crack to the systems, and we have choose alumina, which is very inert in all the atmosphere we have in this case, and this alumina is also very compatible with all the mechanic sample we use on some ceramics. And then, but not the last point is that you have to have a very good contact in between the waveguide and the samples. And I don't speak about that, but due to dilatation when we hate the samples, you must be careful about the breakage of the waveguide, because if you have a sample with a dilatation bigger than the dilatation of the alumina, it can happen. So this is one other limitation of the system. So I will thank you, and also thank you the people who work with me on this subject: Morlaj, Marina Lasser, Jinan Tarabé, Richard Pogo, Eric Seris, Michel Cournil, and Michel Pijola, and people from the partners: François Grosjean, Jean Pitel, François Hopital, Christian Duriez, and Olivia Coinot. Thank you very much.